All right, good morning, everyone. Let me share my screen. Let me know if you are able to see it. Able to see it? Thanks, Boris. All right. Okay. So we were last time we ended the class, the GAN class with Wasserstein or Earth mover distance, and the um, and the reason why we wanted to go with this kind of distance is because there was a inherent problem with uh, the F divergences, be it the KL, be it the Janssens Shannon or whatever it is. So the key problem essentially is that uh, I mean, if there is no support, then and that particular performance, if there is no support between the matrices, between the distributions, it fails miserably. Okay. And so we went to this kind of distance, and without going into the mathematical complexity and everything, just understand one particular aspect, which is that unlike the other divergences where it was a ratio, and because if the denominator becomes zero, that is the support for the proposal distribution or one of the distributions becomes zero, and then it becomes the error becomes infinity and all those sort of things, and undefined or infinity, whatever it is. So now here, or as you can see, it is nothing but a distance between an L1 distance between 2 points. All right. And since it is a L1 distance between 2 points, obviously, what will happen? Even if the support is missing, the maximum distance that we can have is basically theta. All right. And it is a much more smoother distance measure that we have. And essentially, that is the reason why we went for the versus time distance. And we discussed all these things earlier. The one of the key problems, and I mean, you all have by now you all have kind of figured it out through various discussions in the past, is that the primal form of this particular thing is essentially, I mean, even for this particular thing is essentially hard to solve. All right. And because we don't know P of X and P of Y. Right. So what we need to do essentially is we need to use this Kantorowicz-Rubinstein duality. And this is the form of the duality that we have. And if you can see this is basically the Wasserstein distance, and you have a supremum and the expectation of x from P, f of x minus this. Okay. The only constraint that we have to put in in this KR duality is we should use a Lipschitz constant. All right. So the Lipschitz constant should be less than one. Okay. And why the Lipschitz constant should be less than one? I mean, for those of you who know what is a Lipschitz constant, it is fine. For those of you don't know, I'll just give you basically what I mean, tell you what is basically Lipschitz constant or Lipschitz function. So any function f belonging to Rn to R is called a Lipschitz function if it does not change rapidly. Okay. So when we say Lipschitz, a function is Lipschitz, it means that there exists a boundary on the slope of the function. All right. So what we want to say here is that f of x minus f of y is less than equal to k into x minus y minus y. And this essentially is basically the definition of Lipschitz. So now you know that f of x minus f of y divided by x minus y is nothing but the slope. And then we are putting a boundary on the slope. And many of you who have taken, I mean, I know all of you have taken this, but um, you have studied in deep neural networks and other subjects as well, things like vanishing gradient, exploding gradient, and all those, especially the exploding gradient stuff, right? Where you get where you get where you get a non where you get a non what you call um, not a number, right? And your back propagation fails. And so in those kind of cases, what do? You remember what you do? You do basically gradient, you do weight clipping or gradient penalty and all those stuff, right? Those are nothing but practical forms of Lipschitz. Okay. So essentially, why we want to put Lipschitz is because we want to put a constraint on the slope. We don't want a steep slope. If it is a steep slope, then we lose the signal. So remember that the slope of a secant line, basically between 2 points, gives us an approximation of how the function behaves between in that particular region. Now, what happens is, I mean, uh, if if the slope is very large, then what will happen is you will face some problems doing taking your gradients. All right. So we want to limit the gradients to a range so that the signals are more clear. All right. So this is the constraint that we have. And ultimately, this is the practical form of the Wasserstein GAN. And if you see, it is almost the same thing that we used earlier. It's just that, I mean, so Wasserstein GAN with the discriminator d phi x and the generator g theta x is given like this. And there is a Lipschitz of d phi x is enforced through weight clipping or gradient penalty. All right. And now, because of all these mathematical things that we have talked about, we will have support for all the regions. The only thing that we have to take into consideration is essentially the Lipschitzness. Okay. Now, let's see why visually why this is helpful. All right. So the reason why it is helpful is, and just see this particular graph here. On the left hand side, you have the density of real samples. Okay, this is a Gaussian of real samples. On the right hand side, you have a density of the fake samples, the green ones. All right, this is also a Gaussian. Now, when you start your training, there is every possibility that your fake samples, distribution of the fake samples, which will be very different from your or real samples. So now the question that comes here is that our GAN discriminator, our general GAN discriminator, is like this. It is a kind of step function. All right. It is a kind of step function. And in this particular step function, what happens? Everything it will say, this GAN discriminator will say that everything on the left on the left is a real sample. Everything on the right is a fake sample. Right? This is what the GAN is going to do. All right. Now, what is the issue here? The issue is that the discriminator is perfect, so it easily separates real from fake. But the fake data lies in the region where this line is flat. Okay, and where this is flat. And if you want to take a gradient here, the gradient is 0. So the generator receives no gradient signal. Okay, that is, it does not know how to improve, and the train and the basically the training stalls essentially. This is essentially the vanishing gradient problem. Okay, and how does WGAN fix it? WGAN fixes it by having this kind of a critic or a discriminator, that is the light blue line. Now, this WGAN critic line, if you see it closely, it is smooth and approximately linear between the fake and the real regions. Okay, so it assigns higher value to, uh, just don't go by the slide, but it will assign some higher value to the real samples and lower value to the fake samples, basically as required by the Wasserstein objective, essentially. All right. And now, importantly, you see that the WGAN critique is one Lipschitz, that is slope bounded, and it cannot have sharp steps, because we want to avoid these sharp steps because we lose the gradient there. Okay. So the gradient of the critique is non-zero across the regions, even far from the real data. So this gives the generator a clear signal of which direction on to go and what is better. And this is where this kind of intuition comes into the picture. Okay. So more stable training, less mode collapse. This is what the WGAN and this is what the WGAN does. All right. So now what we have done here is we have gone through the entire machinery of GAN. All right. And remember one thing, there are various forms of GANs which are available, because everywhere when you come up with a new model, any generative model, there are various versions of generative model, flavors of generative model that come into the picture. That come into the picture. Now the question is that um, what we did, what we essentially if you just build up the story for 5 minutes here, and summarize the story till now, what we did is we said that we want to go towards likelihood free learning. And why we want to go towards likelihood free learning? Because we found out that in real world, unless and until your f theta matches your f data, you will only in that particular case, the quality of the samples will be very good, uh, and when your maximum likelihood estimate is highest. However, in real life, we know these two are approximations. We cannot exactly match them. And that is the reason why we saw that even with a 99% noisy model, we saw that the sandwich is very narrow, which was log 4 units. And we kind of came to a conclusion that the sample quality is not directly related to maximum likelihood. And that is the reason why we wanted to go towards likelihood free learning. And that's where GAN came into the picture. And when GAN came into the picture, we saw that GAN is nothing but it consists of a generator and a discriminator. And it's a min-max problem that we are trying to solve. And in the min-max problem, the generator is trying to fool the discriminator, and the discriminator is trying its best to distinguish between the fake samples and the real samples. And we will come to us during training, we'll come to a state when the discriminator is completely fooled. It does not know which is a real sample, which is a fake sample. In that case, we conclude that both the real samples and the fake samples that were there come from the same distribution. And that is the moral of the story. Okay. And then we saw that various forms of various divergence formulas. We saw that, whatever vanilla GAN, and we did the mathematical derivation, it came down to Jensen-Shannon divergence. And then we said that already Jensen-Shannon divergence is not the only divergence that is there. There is an entire class of divergence called the F divergence, and we should be able to generalize it across all the F divergence, and we did so. And once we did we so we realized that yes, there is a problem with all these F divergences because it always takes the ratio of the true distribution and the fake distribution, and because in real life you may not have support across both the distributions, similar to the case shown here. What will happen is, I mean, your performance measure will fail. Okay, that is where we needed a smoother objective function, and that smoother objective function was given by Wasserstein in GAN, which is also called the Earth Mover GAN, and we saw that this is the one, and we can also use. All right. So now next question that comes to our mind is, can we do inference here? We have all talked about generation, discrimination, on how to make sure that both the samples are generated from the same distribution and same distribution. Now, this is basically what you call um, I mean, um, however, we have never talked about, can we infer latent representations in GAN? Right. So let's talk a little bit about it. The generator of a GAN is typically a directed latent variable model with latent variable Z and observed variable X. Right? We know that. So the generator takes X from a normal distribution and generates, takes Z from a normal distribution and generates the observed variables X. How do you infer the latent feature distribution in GAN? So we know that in normalizing flow models, we have this kind of mapping, mapping, and but here this mapping which we have is not necessarily invertible. Okay, because for making it invertible, you will have to make some design constraints and all those things. So we want our model to be very flexible. So it may not necessarily be invertible. Okay. And unlike VAs, there is no inference network. There is no inference network like an encoder, which can learn basically the variation in posterior over latent variables. Now, what are the solutions that we have? So the first solution that we have is, for any point X, use the activation of the predefined layer of the discriminator as a feature representation. So this is an old trick that many people use across the board, where people say that as you move forward in a neural network, each of the layer represents different levels of abstraction. And the final pre-final layer that you have in a neural network will represent the highest level of abstraction, which is essentially the best features or more understandable, semantically understandable features. May not be semantically understandable, but we assume that they are semantically understandable features, right? And we can do that. So intuition is similar to supervised deep neural network. The discriminator would have learned useful representations from X for X while distinguishing real and fake X. Okay. All right. Now, if we want to directly infer the latent variable Z of the generator, uh, or we need a different learning algorithm. All right. So if we need to do directly infer the latent variable Z, we need to this. A regular GAN optimizes two sample test that compares X from the generator and the data distribution that we know. What is the other solution that we have? The other solution that we have is to infer the latent representation. We can compare samples of X and Y. So jointly, we can basically compare the samples of X and Y. So instead of just comparing the observed data and the fake samples, we can compare both the X and Y from the observed data and both the X and Y from the fake sample, and basically do a two sample test. Okay, that is one solution that we can have. Now, for any generated for any X generated via the model, we have access to Z. Obviously, we have access to Z, right? So, uh, since we are generating ourselves, our generator is generating ourselves, we have access to Z. We have Z, we have X. For any of the X from the data distribution, that is training data, the Z is, we don't know the Z, and we will need an encoder to know the Z. And that is where this architecture comes in, which is called the BiGAN, right? It is called the bidirectional generative adversarial network. And what it says is, it's pretty intuitive. What it says is, on the top, you have your regular generator. The regular generator takes in Z. That is, this is your basically the fake distribution. Regular takes in Z and basically gives you Z G of Z, which is essentially your X. All right. X, I'm just writing X fake. All right. And it is passed to a discriminator. And what does the discriminator take? So from the top branch, the discriminator takes both the Z as well as both the Z F as well as the XF. All right. That is both the fake latent variable and the fake observed variable. Okay. And from the bottom, what happens is you have your X, you have access to X. Earlier, you were passing this X here. Now, instead of passing only X, you have an encoder network here, and the encoder takes in X, outputs outputs basically Z, which is let's say true distribution, and this is passed here. So now you have a X which is true, you have a Z which is also true. Sorry, which is also true. All right. And then the discriminator does a two sample test here and gives you an output. Now, in this process, what happens is that when you are training your network, what will happen is in this particular process, this encoder gets trained. Okay, so let's go through what is written here. In a BiGAN, we have an encoder network E in addition to the generator network G. Okay, that we understood. The encoder network only observes X belonging to P data X during the training to learn a mapping this X to C. As before, the generator network only observes the sample from the prior. All right. During training to learn the mapping between Z to X. All right. So the discriminator D observes samples from the generative model, that is X and GZ, and the encoding distribution EX and X. Okay. The goal of the discriminator is to maximize the two sample test between both of these. After the training is complete, new samples are generated via G and the latent representations are inferred via E. And this is how you basically how you basically uh, train your BiGAN and you get access to the latent variables. Any questions on this?
So
Sir, last step,
you said that we train the encoder also, but have access to the Z. But how much approximation in this one? Because as we learn, so might be the one-to-one mapping, or maybe the mapping is not so correct.
This is
So,
this will not be a one-to-one mapping. This will not be a inverted, I mean one-to-one mapping. This will be a general encoder similar to what you have learned in autoencoders. It is not a normalizing flow model.
okay, so but how we can say that it is exactly mapping, or what the generator
We
has this
don't
mapping in
say
this?
we don't need to exactly map. Why do you need to exactly map? The only reason, because if you do a deterministic mapping, you are limiting yourself. All right. Typically, whenever an encoder maps, it will map to a distribution similar to what you have in VAE. So that is the reason why there is no point doing a deterministic mapping here. Normalizing flow models was one flavor where we see that we could go forward and come backward. That is one model that we had. But given a choice of models, we would always want to go for a model which learns a latent distribution rather than a deterministic latent variable, because that gives us more flexibility during the generation phase. All right. So now this is the last topic. There are few more GANs which are there in your slides. You can go through them. I mean, these are all different flavors of GAN. You just need to get the inclusion. Now, this is an example of translating across domains. So let's say an image to image translation. All right. So we have images from two domains, X and Y. Okay. Paired and unpaired example. Now, this particular thing comes from the supervised area, especially this one, because someone has taken the pain to basically do the pairing. That is a discolored shoe and a colored shoe. All right, they are the same. And these are unpaired. We don't know. All right. Now, obviously, in a supervised learning situation, this is a relatively easy problem to solve because of the fact that we have these paired samples and we can train our model to do this. But as you all know that supervised data is very expensive, can we do anything in an unsupervised manner? And that's where another type of GAN kicks in, and which is called the which is essentially called the cycle GAN. All right, which is essentially called the cycle GAN. So the cycle GAN and says the concept is very simple. All right. So to match the two distributions, we have two parameterized generative models, G and F. Now, what does G do? G takes X and maps it to Y. And what does F do? F takes Y and maps it back to X. All right. And these are the two discriminators which are there. All right. Now, G maps an element of X to an element of Y. A discriminator Y compares the observed dataset Y and the generated samples G of X, similar to what you did in an autoencoder. Okay, you wanted to reconstruct that. Now, similarly, F maps an element of Y to an element of X. A discriminator DX compares the observed dataset X and the generated samples this. Okay, it's the same thing, but in a reverse manner. And now let's see what happens here. So cycle consistency, if we can go from X to Y via G, then it should also be possible to come back from Y hat back to X via F. And this is exactly the functional form. That is F of G of X is nothing but X. Similarly, G of F of Y is this. And this is basically how the cycle can and works. So you go from X to Y, you come back, you go from X to Y hat, you come back from Y hat to X hat. And basically you have a discriminator which is trying to find the cycle consistency loss. And the similar thing happens here as well. You go from Y to X hat and X hat to Y hat via the G and F function. And then you have a cycle consistency loss here. And the overall cycle consistency loss, without going into the mathematics and all these things, is this. So what this is going to do is this is going to basically do this kind of image translations across the domain in an unsupervised uh, manner. All right. So this is all about GAN. Um, so there are couple of more, I think, star GAN and a few more GAN. You can go through your course, what you call notes. It is there in the later slides as well. But I'll not go through all those GANs because these are just nothing but flavors of the same GAN. The main thing is that you should get an intuition about the machinery of GAN, why why how the entire machinery of GAN works. And then these flavors of GANs are just nothing but tweaks in the architecture just to make sure various problems are solved. Okay. All right. Okay. So, all right. So let's talk about a little bit about energy-based models. Okay. So what we are going to start today is a group of models which are uh, we'll start with energy-based models. We'll cover a couple of classes with energy-based models, and then we'll move to the diffusion models. All right. So what we'll be studying today are energy-based models. Okay. All right. So let's start talking through them. Okay. So this is our old diagram that we have. You all are familiar with it. What we have gone through now are autoregressive models, normalizing flow models, variational autoencoders, right? Everyone had a different flavor. Autoregressive models where your probability was defined by a chain rule that is into product of the conditionals. Normalizing flow models where you had an invertible function, you could go from x to z and z to x. You had variational autoencoders where you did not have direct access to the likelihood, but you took the help of elbow and essentially approximated it. In all these cases, the model architectures were restricted. Okay? I mean, you cannot use any neural network architecture which takes any x and outputs a scalar. Okay? So we cannot take any x, any neural network which takes your inputs, that is x, and outputs a scalar. Okay. And the reason why we cannot do this is because the output has to be a valid probability distribution. By design, all these type of models um, have been, I mean, all these type of models have been designed in such a manner that they output a valid probability distribution. And that is the biggest uh, architectural restriction here. Okay. Then you have we studied our adversarial networks. And in the adversarial network, we just discussed, I mean, in what are the pros and cons, what are the pros and cons we have. And obviously, I mean, they are very flexible model architectures, but likelihood is intractable. Training, I mean, we don't want to go towards likelihood anyway. Training is unstable. That is the biggest problem. They are hard to evaluate and they are suffer from mode collapse. Okay. Uh, so that is essentially the problem with those. So what we will do today is we will study energy-based models. Now, the key thing about energy-based model is they are very flexible model architectures because uh, because we don't put any restrictions on them. They are very stable in learning, I mean, in training. And they have relatively high sample quality, and they have a flexible composition. Okay. Now, the thing is that these models are very closely related to diffusion models, which are the state of art now for continuous modalities like images and audio. Okay. And when we say flexible composition, I mean it means that it can take different kind of generative models and combine them. That is what it is. So let's start building up the machinery and the intuition here. Okay. So parameterizing probability distributions. All right. Now, what is the probability distribution? I mean, mathematically. Okay, mathematically, what is a probability distribution? Probability distribution is nothing but a function which takes x as the input and maps it to a scalar. So you give x and it will give you the probability output of it. Okay. And probability distributions, basically, as we have seen now, this is the 11th class, I guess. Uh, Throughout all the 11 classes, we have seen, we have only talked about probability. We have mostly talked about probability. Okay. And as you can see that for generative models, probability distributions are the key building blocks. Okay. And probability distribution cannot be any arbitrary function. I mean, a probability function cannot be any arbitrary function. It has to satisfy a few rules. The first rule is that, or constraint is that it has to be non-negative, because your probability is always greater than equal to 0. The second rule is that it has to sum to 1. The entire distribution has to sum. The probabilities of the entire distribution has to sum to 1. Okay. Obviously, this is in case of the discrete case and integral in case of the continuous case. All right. So this particular problem, which is non-negative, is a very uh, simple problem to solve. Why? Because you have so many functions like these, right? X squared, exponential, you take the absolute value, log, all these functions will basically give you a non-negative output. And there is absolutely no problem with defining this kind of function. But the whole issue comes with this particular part, which is hard. Point number 2. That is, it should sum to 1. All right. And the key thing is that we want to define a probabilistic model, and which means having a probabilistic distribution. And if we couple this with a loss function, we get a new generative model. That is what we have been doing till now. So what we want to do is that, listening to it uh, carefully again, we want to define a probabilistic model. Okay. A probabilistic model obviously will have probability distribution. And if we couple this with a loss function, we get a new generative model. And that is what we have been doing here, right? I mean, and we have we want to define a probabilistic model. This is your probabilistic model. And obviously these probabilistic models will have a probability distribution. Okay. And if we couple this with a new loss function, this particular thing, we get a new generative model. Yeah. And that is how we have been doing the entire thing. So these probability models were nothing but neural networks, and these were nothing but things like KL, Jensen, Shannon, your GAN, and all those GAN. I mean, likelihood free learning, XYZ, FGAN, and all those particular stuff. Okay. All right. Now, we have talked about these 3 points. Now, remember one thing is that whenever we are talking about probability, uh, the entire volume has to remain the same. So it means that your total volume is fixed. Now, if we increase the probability of a point, it means that the probability of the another point or some other points will have to go down. Okay. So it cannot be that you have a slice of pizza here or cake, whatever it is, and you increase the size of one slice and the other slices, the size of other slices will not change. It has to change because ultimately this cake or pizza, whatever, the size, the volume of this is the same. I mean, fixed. All right. And that is the key challenge with probability. All right. Now, as we have said, this is an easy problem to solve, but your g theta x might not sum up to 1. Okay. And if your summation overall x of g theta x is equal to z theta, we will, going forward, we'll denote it like this, is not equal to 1 in general. So this particular function is not a probability mass function or a probability density function. That is the whole problem. All right. So now let's see how we go about it. So if you see here, if you see here, uh, our problem statement is basically this. All right. And how does the solution go? So this is what it is. So probability of x give, all right, is equal to g of x divided by z of theta. All right. What does it mean? This particular thing in technical language is called a partition function. In in general literature language, this is called a normalizing constant. Okay. So your probability distribution is your numerator, which is this function divided by your partition function or normalizing constant. Normalizing constant is nothing but, if you take the case of continuous variables, it is an integral of g theta x dx, right? And this ultimately represents the volume of this. Okay. Now, the, then by definition, then by definition, your integral of p theta x, what is your integral of p theta x? Your integral of p theta x is again your integral of this entire thing, this entire thing. All right. And if you go to the, if you take the integral of the top portion, I mean, if you take the integral now, this, what you will get, it is z theta by z theta, which is equal to 1. So basically, it means that your probability should sum to 1. Okay. Now, the question is that from our statistics, we have we talked about closed form solutions and all those particular stuff, uniform and all those particular stuff, right? And if you remember, if you remember that um, what you call how does a multivariate Gaussian looks like? So how does a closed form multivariate Gaussian looks like? Okay, the closed form multivariate Gaussian looks like this. And if you remember, it looks like this: 1 by square root of 2 pi sigma square e to the power minus x minus mu whole square twice sigma square. This is the formation of a PDF for a multivariate Gaussian. And we all know this function. We all have seen this function at various points of our career. Okay. Have you ever thought about this particular fact, that where does this particular thing come from, and all those things? Now this nuance can be seen from here. So if you see here, your probability, your function is is this. And typically we always want to go with exponentials, and I'll tell you why later. Because of one is non-negativity, but there are other aspects as well. Now, if you take the integral of this, the integral of this particular thing boils down to this. Okay. And you see what is the formula here? G of theta x divided by z theta, which is essentially your this. So this is your normalizing constant or your partition function. Okay. So now you know, if someone gives you a closed form, I mean, if someone gives you a multivariate Gaussian and you see the closed form Gaussian formula, you will know where from this constant, this weird looking constant is coming. It is because we have taken the integral of uh, g of x. All right. Similarly, uh, similarly, we can take this particular, for exponential also we can and do the same. I'll not go into it. And for those who have done, I know this was never a part of machine learning, but ideally it should have been. But there is a broader family of functions called exponential family. Okay, from where everything in descends. All right. So if you go toward to the I mean, if you want to generalize this particular form, this is the generalized form that you have. You can go through the literature and you can see that this is the generalized form of the exponential family. And Gaussian, Poisson, exponential, Bernoulli, all are nothing but variations of this. Okay.
One
Now,
question, sir.
yeah, go ahead.
Yeah. So the where we have the square root 2 pi sigma square Gaussian
Mm,
one. So we
mm.
have taken the integral of e to the power minus x minus mu square, right? But in integration, we don't have that square at the numerator. Yes.
Sorry, can you repeat once
Uh,
more?
in the integral of e power minus x minus mu, the x minus
Mm.
mu, does it have a square there or
It has a square there. It has a square there. This is wrong actually.
wrong? Okay, got it. Thank you.
Okay? Yeah. So um, all right. So now the question here is that, I mean, we now see that every probability density function, be it normal, be it Poisson, be it exponential, or any other, has this particular form, which is P of x is equal to g of x divided by z of theta. All right. And because we know the analytical form or the closed form of this, we can define it in this particular manner in case of a Gaussian, in case of exponential, and then there is a generalized form. Okay? Now, the question is that function g theta needs to allow analytical integration. Okay. If this integration was not possible, we could not have calculated the z theta. We could not have calculated the z theta. All right. So, I mean, in real life, in real life, this particular integration will not be possible or will be computationally very expensive. Okay. So now that is the reason why we still cannot choose any arbitrary g theta. And this is where EBM comes in, where we want to define a neural network which are much flexible and analytical form may not be known. Okay. The analytical form of the neural network may not be known, but we still want to use this machinery. Okay. And the way in which we are going to do it is, uh, let's talk a little bit about it. We are going to basically first see how we can do it using the likelihood based learning. Okay, so this is our problem statement, which is g of theta x is greater than 0, but this is hard. We have seen this. We saw this. Now, why does our autoregressive models work? Now, in autoregressive models also, we had a neural network and we never cared about or whether it outputs a probability distribution or not. And the reason why we did not care about that particular thing is because let me just get a uh, empty page. Okay. Now we are talking about autoregressive models here. And the reason why we want to talk about autoregressive models first is because we are now saying that we want to output a probability distribution. Now, the output of a neural network does not necessarily will be a probability distribution. There is a partition function which is there. We have to take the integral of the numerator, which will be the partition function and all those stuff. But we never talked about all those stuff in autoregressive models. We simply use the chain rule and move forward. Okay. And let's see why we never talked about it and why it was fundamentally principled. Okay. Now, now the question is that P of X is what? It is the probability of a point X. All right. This is the probability. And this is also called basically the marginal distribution, right? And when you integrate this P of X dx, this will be 1. And this is basically nothing but the normalization of the marginal. Right? Because the total probability of all values will be 1. Now, when we say probability of y given x, what do we mean by this? We mean that conditional probability of y given a fixed value of x. All right. And what do you mean by this? Sorry, this is not f, this is integral. So it means that for a fixed x, the total probability over all y's is 1. So that means for a fixed x, okay. Now, these are the components, okay. Now I tell you, what is the joint probability between x and y? Joint probability of x and y is given by this, the prior into this likelihood. Okay, this is how the joint probability prior into conditional. This is how the joint probability is given. This captures the full distribution. This captures the full distribution over all pairs of x and y, right? So this captures the full distribution over all pairs of x and y. All right. Now, what I say is that what will happen if I do this? Normalization of the joint. Okay. Now, this can be written like this. Right? And this can further be rearranged like this. And now you see a nice thing happening here. This particular term here is 1. This particular term here is 1. We have seen this. We have seen this. And this is actually 1. All right. So that means the total probability over all x and y is equal to 1. And this is exactly why the autoregressive models by design were were giving a probability distribution rather than a unnormalized distribution. Okay. So in neural network setup, it is also written as, I mean, normally if you go to the slide, the nomenclature is a little bit different. If you see the nomenclature, what is the nomenclature? P of theta, P of theta, P of theta, it's the same thing. P of theta x is a distribution over x parameterized by theta. And this particular term, which is P theta prime x y, is a conditional distribution over y given x parameterized by theta. All right, this is basically the decoder. So now you don't need to be confused about this. You just go through this. This is exactly why your autoregressive models work, because they were, I mean, the output was a probability. The output it was outputting a probability distribution because of the nature in which what you call um, we designed the network. Okay. Now the other thing is that autoregressive models were product of normalized objects, and the product of normalized objects were normalized. And in latent variable models like the VAE or the mixture of Gaussians and all those particular things, this works in this particular manner. which is, I mean, this takes this functional form, which is alpha p theta x plus 1 minus alpha p theta x. There are two mixtures. And if you take the integral of this, you will see that the integral L comes to 1. And that is the reason why we never bothered about this normalization constant, because by design we were doing something which outputted what you call normalized distributions or the probability distribution. But now I mean, the more flexibility you give, the more architectural changes you want to do in a neural network. Obviously, you cannot live with this particular constraint, which is by design you make the output normalized, and you have to do something where you always cannot solve these things analytically, and you want flexibility in your network. And how do we do it is going to be answered by EBM. All right. So in EBM, as we have talked about, in EBM, we have these two components. One is basically the numerator, which is basically called the what you call um, um, I mean, this is basically the exponent, the function. All right. And the other thing is that you have your partition function, which is your denominator, which is hard to this. And your denominator is nothing but an integral of all the values of x, right? Over all the values of x. Okay, the first question that we want to answer is, in lot of literature, you will see that the numerator in a probability distribution or in this kind of situations is always an exponential. Okay. And why do we want to use an exponential? We could have used square. We could have used a lot of other things. Why do we use exponential? It is because the key reason is because the exponential functions grows or shrinks very rapidly. Okay. So if you were to take, let's say, d of x expo exponential of f of x, this is going to become f of x into exponential of f of x. Okay, this is close bracket. This means what? This means that the rate of change of the exponential function is proportional to both the slope, which is this, as well as the current value of the function. Okay, so even if f of x changes slightly, e of exponential of f of x can change a lot, especially if f of x is already large, all right, positive or negative. And this is one of the key reasons why we want to use this particular function. Okay. And the key thing is that, I mean, obviously we said probability distribution has to have positivity. This fulfills the positivity. This also gives you flexibility in shaping, because of the rapid growth and decay. Exponentials basically allow us to model sharp peaks and concentrated probabilities easily. Okay. And obviously smooth gradients, because exponential is differentiable. All this. Yeah. So this is the reason why we use exponentials a lot. You have an entire family which is exponential called the exponential family. Okay. All right. Now, remember one particular thing here is that this particular group, this particular class of functions is called energy functions. All right. And it is one of the oldest one of the groundbreaking fundamental work that was done earlier. And this is the class of models for which Geoffrey Hinton and got his Nobel Prize. So he worked on deep Boltzmann machine or restricted Boltzmann machine for whatever he got. But those Boltzmann machines are nothing but energy-based models. Okay. Now let's talk about the core idea here. The core idea is that uh, now what we have been doing in autoregressive models or the latent variable model is basically to cleverly combine normalized objects essentially by putting restrictions on the neural network architecture so that, I mean, we get a probability distribution which equals to 1. All right. And what energy-based models do is to get rid of this particular restriction and go beyond your PDF or PMF. Okay, this is what it is. And obviously, PMF and or PDF are guaranteed to be normalized. And this is good in case where you are able to calculate the normalizing factor analytically. Okay. Now, here, remember one thing, instead of directly predicting that this is a cat or this is a dog, the EBM will ask a question, how well does this input fit what I have learned? Okay. Now, the key thing here is that EBMs are called energy-based model because they define essentially a scalar energy function that assigns low energy value or to likely or desired functions. Now, remember, if you, for those who remember your physics and all those things, you remember that in physics, molecules tend to be stable in equilibrium in low energy. As the energy becomes high, what happens is that the molecules are no longer stable. So the ideal state where we want I'm just taking an, an example here. There can be a lot of other examples from physics, but uh, if you remember here that, for example, in probability, uh, what is the desired state? We want high probability. We want to sample from high probability regions. That is our desired outcome. In case of energy, when we are talking about energy in physics, the ideal state is low energy. All right. The ideal state is low energy. And that is the reason why this particular class of models is called energy-based model, because this exponential function will give an output. I mean, this particular the the function that the exponential that the exponent takes will have a negative sign here. Okay. And the reason it has a negative sign, because we want to say that lower energy means higher probability. Lower energy means higher probability. So intuitively, the configuration X with lower energy, higher effects are more likely. So that is where from this idea has been borrowed. So essentially, this terminology, if you talk about this terminology comes from essentially statistical physics. All right. So, I mean, we, if you still recollect, the energy functions basically describe the probability of the different states or in a physical system, right? And in physics, the system tends to tends towards lower energy state, and the probability of finding a system and basically in a particular state is related to its energy, okay, through the Boltzmann distribution. Okay. And this energy function will map any input configuration to a scalar representing its energy. So what the model will do, and we are not talking about a probability distribution as yet, all right? What the model will do here is that The model will learn to assign lower energy to data points that are likely or good, and higher energy to data points that are unlikely or bad. Okay. So essentially, your, your probability distribution is going to be proportional to e to the power minus, this is a function, energy function, x. Okay. It will become clear as we move forward. Meaning that lower energy corresponds to higher probability, lower energy corresponds to higher probability. Okay. So in EBM, the key thing is that instead of calculating the probability, what we are interested in is calculating this. All right. So the key thing that we are going to work around, and the key trick that we are going to do here, is that instead of concentrating on this probability, if we can somehow bring our mathematics towards the fact that we can look into only these things, then we are not anymore bothered about your partition function. Okay. And that is the trick that we are going to apply in one way or the other. Okay. Now, what are the pros of energy-based models? And we are just now scratching the surface, all right? What are the pros of energy-based model? Extreme flexibility, can pretty much use any function you want, okay? What are the cons? Obviously, sampling is hard because we don't know p theta x. We don't know the partition function. How can we sample? Evaluating and optimizing the likelihood is again hard, which means the training is also hard. Okay. And there is no feature learning, but yes, there are certain workarounds by which we can get over it. So I mean, while we on one side, we are saying that this will give extreme flexibility, but now on the other side, we are saying that two of the most important functions that we expect out of a model, sampling and learning, are very hard. So what can we do? All right. So the fundamental issue in this entire thing here is that, I mean, computing your z theta numerically, okay, when there is no analytical solution is available, it scales exponentially as the number of dimensions increase. All right. So your numerator, if there is a closed form, it is fine, but closed form are there for very basic functions. But in a complex structure like a neural network, you don't have a closed form. And obviously you have many, many dimensions which we work on which we work on. And this is essentially, what you call, uh, um I mean, the problem. Okay. And if you see in one way or the other, it is the same problem that we faced even in what you call VAs, right? Even in VA, the denominator, that is the marginal, was very difficult to calculate. It was intractable. Here also, it's the same thing. This is intractable. Okay. But we are going to um, and the whole idea of energy based models is we are going to take an arbitrary neural network which has a functional form f theta x, all right, and take an exponential of it to make it non-negative and divide by a partition function. That is the fundamental. Okay, we want to take any function. We want the flexibility. We want to take any function. We want to exponentiate it to make it non-negative. All right, and then divide by the partition function to normalize it. But the whole problem lies here. But one of the key things you will realize in this entire discussion is that some of the things for some of the tasks, we really don't need the normalizing function. How? For example, we have this, but this is our functional form, right? Now, given 2 points x and x prime, evaluating p theta, evaluating p theta or p of evaluating p of x and p of x prime requires z theta. But do we need this particular z theta when we are doing a ratio? No, because the z theta will cancel out. All right. So this means that there are a lot of use cases we can solve using this technique, because we can compare two samples. We can always compare. We may not be able to um, calculate the probability of that particular sample, but we can always compare whether one sample is better or worse than the other. This means that comparing the probability of any 2 points does not require us to know the normalizing constant z theta. Okay. Now, having said that, there are a lot of applications where anomaly detection is something which you can always do a comparison, denoising, and all those particular stuff. Okay. And few examples are given here. These are quite primitive examples. I mean, energy-based models have been used for object recognition. Energy-based models have been used for sequence labeling, image restoration. And so, I mean, there is a lot of areas where energy-based model can be used. I mean, as long as the function requires relative information, the partition functions are not needed. Okay. For example, you want to say whether it is a cat or a dog, right? So if you are able to compare compare the relative information, the partition functions are not needed. Okay. All right. So a few simple what you call uh, uh, architectures of energy-based models. We'll come to the complex ones later. Is I mean, the first is basically the Ishig's model. Okay. Now, model. This is a very primitive type of thing, and so you have a picture here, and this is the actual picture, and so there is a true image y. This is a binary image 3 by 3, and a corrupted image x 0 and 1, again binary 3 by 3, and we know x and we want to somehow recover y. Okay, so the true image is y and the corrupted image is x. We know x and we want to recover y. Okay, now see the architecture of this particular model. I mean, what exactly it is doing. So in the yellow, you have all your y's. All right, 3 by 3, all your y's. Y is what? Your true image. And the green are the ones which is essentially your x's, which is your this. So x are the noisy pixels and y are the true pixels. Okay. And we want to model the joint probability distribution of p of yx. All right. And how do you basically model the joint distribution of p of yx or p of y and x? It's the same thing, right? 1 by the normalizing constant into exponential of, and this is the structure, which is this particular expression tells that the ith corrupted pixel depends on the ith original pixel. All right. And this particular thing says that the neighboring pixels tend to have the same value. Okay. So YY and XI. So the ith corrupted pixel. So how did the original image look like? Solution: maximize Y given X, or equivalently maximize Y and X. Okay. So let's go through this go through this once. I'll just take a blank slide and write something. All right. It'll make your intuition a little bit more clearer. Okay. So in this model, what we were doing basically image denoising. All right. X was your corrupted or noisy image, and Y was your true image. Okay. The key insight is that we need to model the relationship between the corrupted and the clean images. That is what we want. We just cannot model. If someone tells you model P of Y, that is your uh, uh, true image, we can, there is no use of this. What we want to do is we want to model, sorry, P of Y and X. All right. This is what we want to model. Why? Because if we are able to model this particular thing, then only we can do some form of denoising. Okay. So we just can't model P of Y alone, because that would ignore the information we have about the corrupted image. All right. Now, from our discussion about the energy-based models, we know that the functional form of a joint distribution is in an energy-based model is something like this. This. All right. And in the earlier slide, if you see here, they said we want to maximize probability of Y given X. Okay. Now the question comes is why we want to maximize probability of Y given X. The reason why we want to maximize probability of Y given X, because maximizing probability of Y given X is the same as maximizing probability of Y in X. Why? Because we know probability of Y given X is equal to probability of X and probability of Y divided by probability of X, right? And since we are trying to find the best Y for a fixed observed X, the term P of X is constant with respect to Y for all the observations, right? This is constant. So when comparing different possible clean images, okay, so there are different possible clean images, Y1, Y2, Y3, and so on and so forth. What we have is probability of Y1 given X is proportional to probability of Y1 X1. Probability of Y2 given X is proportional to probability of Y2 X2, and so on and so forth. So the solution becomes find the Y that maximizes the unnormalized joint probability, which is equivalent to essentially minimizing the energy function. So this is essentially what these guys are doing in the Ishin's model. Now we come to the second type of a second example. This is also a very simple example. It is essentially the product of experts, right? It is essentially the product of experts. All right. So the key issue is that suppose you have trained several models Q1x, Q theta, R theta 2x, T theta 3x. They are different models. I mean, pixel, CNN, flow, whatever. Each one is like an expert that can be used to score how likely an input is. Okay. Assuming the experts make their judgment independently, it is tempting to ensemble them in this particular manner. Okay. But to get a valid probability distribution on essentially, this will be, but to get a valid probability distribution, we'll have to do this. Okay. So what are we exactly saying? The key issue is that individual models are modeling different things in case of product of experts. So in an autoregressive model, what do you have? You have this kind of thing. Okay. Each factor is conditional probability given the previous tokens. That is what it is. And they are designed to multiply together to give a valid joint probability. We saw that earlier, right? So no normalization is needed. But in the product of experts, each expert, that is, I mean, Q theta, R theta, T theta, is modeling the same thing. They are trying to estimate P of X. All right. They are actually not conditional probabilities that naturally multiply together. Yeah. So if Q of X, if let's say if Q of X and R of X are both normalized probability distribution, all right, their product does not need to be does not have to be normalized. Okay, so that is the reason why what it is saying is that, I mean, you can use this kind of model is also a energy based model, because your output cannot be in the form of a probability distribution unless and until you plug in your what you call z theta, right? All right. And this is some examples of how people use a product of experts. So if you see on the top, there is a EBM which basically tries to generate young people, and then you have an EBM which tries to generate young and female, and then young female smiling, and then young female smiling wavy hair, and you see that they are doing a uh, pretty decent job in terms of what and this is by the way, this is an old model, right? So pretty a decent job. I mean, energy based models are doing a pretty decent job. Yeah. So so the whole conversation the whole conversation now is revolving around the fact the whole conversation now is revolving around the fact that we cannot calculate the numerator, and sorry, we cannot calculate the denominator, which is the partition function, and we cannot work with the probability distribution, but we have to work with the numerator, which is basically an energy function called the energy function. And if we are able to do certain kind of tasks, if we are able to do certain kind of tasks which are mm, which are essentially which do not essentially need the normalization constant, then we are in good space and we can use this type of this type of uh, model. Okay, and that brings us to the restricted Boltzmann machine. Okay, now no longer in favor, no longer used, but it was a groundbreaking work that was done. So this is an energy-based model with latent variables. So binary energy-based model, your X and Z were both binary. So X is 0, 1, and 0 and 1, and n dimensions, and they are visible units and visible variables basically. And your Z are basically the hidden units. And the joint distribution of this particular thing is essentially again the same thing, um, which is 1 by Z exponent e to the power x to xt. So what it is doing is, this is x, this is z, these are your w's, and then you have a bias which is b, and then you have a bias which is c, and this is what. So what it is doing is, the connection between x and z is controlled by the weight w, and that is why it is taking and multiplying the vector x with a matrix w, and then again with the vector z. And then you have your x, which is multiplied by the bias, which is your visible unit. And then you have a c, which is multiplied, sorry, z, which is multiplied with c, which is this. And if you see here, it is just the expanded form of this. So 1 by z exponential of, it's the summation of 1 to n and the summation of 1 to m and this. Now, this is a model which, I mean, the predecessor of this particular model, that is the Boltzmann machine, was there for a long time. And what restricted Boltzmann machine did was, restricted Boltzmann machine just removed the connections between these. Okay, and they made all of these states independent, right? And this particular thing is actually, if you go through the literature, this is actually not a model. This is a building block. Okay, this is a building block. So before this came into the picture, deep neural networks were very difficult to train. All right, because of this vanishing gradient problem. Okay, now once this building block, was defined, and I mean, there is a huge literature on restricted Boltzmann machine, deep Boltzmann machine. You can go through it, but I mean, if you are interested, but we'll just cover it at a high level, and because of the fact that this is no longer used, okay, so we have better things to talk about. But the whole objective here is that, um, I mean, what you do is, you basically train your model to get these weights. All right, to get these weights, to get these optimized weights. Once you get these optimized weights, then what happens is, these units become your visible units, and you again train a model, again train another layer, which is essentially your um, and this one you will call hidden now, and this one you will call visible now, and you train another layer. And finally, what you do is, I mean, empirically, it has been shown that if you stack up these layers together, what is going to happen is, you are going to be able to train a neural network without the vanishing gradient problem, because you have already pre-trained these stacks prior. And that is what is essentially nothing but the deep Boltzmann machine, which is this. All right. So in earlier days, your deep neural networks, I mean, in supervised learning, had to be pre-trained this way to make them work. All right. So, and why they are energy-based models? They are energy-based model is because this particular form. Okay. So this is essentially the deep Boltzmann machine. If you all are interested in learning about this Boltzmann machine. There is some literature, good amount of literature which is available. You can get a hang of why this was invented in the first, I mean, discovered in the first place, and how it moved forward. But now there are better things to do, and this is essentially uh, where we will go towards. Okay. So this is the slide that we saw earlier. Can EVM can plug and play any function. Sampling is hard, training is hard, no feature learning. We can do that. Curse of dimensionality. Okay. Because in calculating z of theta, now what do we do? Okay. Now the question here is that computing the normalizing constant, is actually hard. Okay. So let's take an example. So the RBM joint distribution is like this, where these are the visible units, and the normalizing constant is this. Now, note that it is a well-defined function of parameters W, B, C, but no simple closed form. Okay. Takes time exponential in n and m to compute. This means evaluating the objective function for this is very hard. Observation, optimizing the likelihood, that is, this is difficult, but optimizing the unnormalized probability, that is this, with trainable parameters W, B, and C is easy. And that's where we are heading here. Okay. What we would be doing now is uh, something called, and we are going towards it, is something called the contrastive divergence. Okay. We'll go towards contrastive divergence. But first, let me give you the intuition, and probably I'll stop the lecture here and we'll go to the mathematics of contrastive divergence later. Okay. So what happens is your this x-axis is nothing but your data points. Y-axis is basically your f theta. And what is your goal? The goal is to maximize. I mean, we know from maximum likelihood, the goal is to maximize this. And when you want to maximize this, one thing you need to remember is that you have to increase the numerator and decrease the denominator. All right. Why? Because, I mean, it's the same pizza slice story, right? It cannot be that you have increased the probability of a particular point, but you have not decreased the probability of another point. Okay. So whenever you are increasing something in the numerator, you have to decrease something in the denominator. Okay. Now, because the model is not normalized, increasing the unnormalized log probability f of theta x train by changing theta does not guarantee that x train becomes relatively more this. We also need to take into account the effect on other wrong points and try to push them out to also make z theta small. Okay. So what it is trying to say here, what it is trying to say here is that you have this particular point which is correct, this particular point which is wrong. You want to increase the probability of this particular point. So if you have to increase the probability of this particular point, somehow you have to do something to decrease the probability of the wrong point. All right. And essentially, this is essentially what we do in contrastive divergence. And here in contrastive divergence, my goal is to maximize this. Now, instead of evaluating z theta exactly, we use a Monte Carlo estimate and contrastive divergence algorithm. Sample X sample from P theta, take a step in this direction, making the training data more likely, than typical sample in the model. All right. And I think let me go through one more slide with the maths, because that will actually be better, actually be conclusive, right? So this is the maths. Okay. So what are we doing here? My model, my model was essentially this. My model was essentially this. Um, I'm just putting this. P of theta x is equal to exponential of f theta x divided by z theta. This is my model. Okay. Now, whenever we are doing log likelihood, what we would do is we would basically take the log of this. Sorry, log of p theta. Okay. And if we take the log of p theta x, that side also will take the log. And this will be log of exponential f theta x by z theta. And this log and exponential will cancel out. And what we'll be left with is f of theta x minus log of z theta. Right? This is what we are. And this is exactly what it is. So we want to maximize this log likelihood. Now, to maximize this log likelihood, what we have to do is, and remember, this x is extreme. What we have to do is, we will have to obviously take the gradient. So we take the gradient of this term. We take the gradient of this term. And obviously, what will happen is, now from standard calculus, you know that sorry. This is exactly what has happened here. All right. So the derivative of the log of a function is equal to the derivative of the function divided by the function. All right. Now, once you have this, what will happen? We are not touching this expression. This expression remains the same. We are only working on the right hand side. So now I can pull 1 by z theta outside. All right. And I can write this as this. All right. So what did we do? We have just used the integral form of the normalization. Okay. We have just used the integral form of the normalization. Now, once you have this integral form of the normalization, you can basically do a small little bit of rearrangement and bring this to an expectation form. And now what has happened here is that you have an expectation of a sample of X sample, and inside it you have the gradient. And we can use Monte Carlo approximation here for a single sample, and we can basically write it in this particular manner. Okay. Now, the question here is, the trick here is that or the key concept here is that as long as we are able to follow the gradient, as long as we are able to follow this gradient direction, we will converge. All right. Now, the thing here is that we have this as a part of our training data. How do we get this? Because we don't know how to sample. All right. We have come up with a algorithm called the contrastive divergence, via which we have got rid of the z theta in this entire exercise. All right, in this entire algorithm. But now we are stuck in a place where we cannot calculate, we cannot do sampling because uh, 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 because I mean, when we are, it is only possible. I mean, all this training is only possible when we can generate samples from the model. If we are not able to generate samples from the model, what are we going to do about it? Okay, we cannot do contrastive divergence. So that's where we take a pause for this week. Next week, what we will do is that uh, we will see how we can sample from energy based models. There are various techniques in approximation techniques by which we can sample from energy based models, and we will see uh, where we go from there. So the key thing to note here is that in contrastive divergence, the loss we are minimizing is something contrastive. That is, we are pulling down one value and pushing up another. Okay. So essentially what we are doing is we are essentially doing this, right? This. And this is basically the gradient vector. This is basically the gradient vector. Gradient vector, and this gradient vector, if you it is just like any other gradient vector. This is a direction in the parameter space, but now it has two competing forces. One force is pulling theta to decrease the energy level of the real sample x train, okay, and the other is pushing theta to increase the energy level of the fake sample, that is x sample. Okay, so remember, one thing is that theta is a point in a high dimensional space. The two gradients are the two scores in the parameter space essentially. And the difference vector is the result of vector subtraction. And we move along the direction just like standard gradient descent. Okay, that's the entire crux of the matter. So now what we have done is we have found out a algorithm to train the model. We have found out optimization technique to train the model without the need of without the need of calculating the z theta. Our next step is that how do we sample from the model? How do we sample from the model so that we can do we can do basically contrastive divergence. Okay, so this is the uh, machinery that we are talking about today. Okay. All right. So any questions? Okay. So then what we'll do is we'll continue with contrastive divergence next week. Sorry, not contrastive divergence, but energy based model and all those things. And we'll see where we go from there. Okay. Thank you.
Thank you, sir.